In this lesson, we're going to learn how to balance redox equations. Now, this is leaping ahead a little bit. You will cover this in your second semester analytical course, but we need it right away, so I'm going to cover it now, and repetition is always a good thing for something that's considered to be more challenging. And in fact, I should warn you that many students do find this something that requires several swings at it to get a hold of it. So give it your best here. There's a set of rules for balancing redox equations on page 263 of the appendix, but I'm not going to read them to you. I'll simply explain them as we go through this. I should mention too that the material we covered in the previous lecture on oxidation numbers is on page 261 in the appendix, and some EMFs, page 260. Some introductory material about oxidizing agents and reducing agents and oxidation and reduction. It's on page 259. So there's lots of this stuff in the appendix. I'm just kind of, as I say, jumping ahead with it. I want to also mention that on Blackboard, I have a video. It's 40 minutes long. It explains how to balance redox equations. It goes through 3 examples, starting simple and going harder. And I did this years ago because students asked me repeatedly in class, would I teach it again, would I teach it again? I remember one time up to 5 times, and some of the other students said, sir, we don't want to hear it anymore. And I get that. So what I did since then is I made the video. I'll teach it once, and then if you need more repetition, watch the video. So in this first reaction, we're going to look at the oxidation of methanol, methyl alcohol, with potassium permanganate. Let me write out the equation. I'll explain what these pictures are about. Methanol, or methyl alcohol, is CH3OH. The OH in an organic alcohol is not negative. It's not hydroxide, so it behaves differently. It's more like the OH in water. In fact, alcohols are very neutral. Now, potassium permanganate is this purple, dark purple liquid that you see on the left. It's best to leave out spectator ions like potassium because it just causes more grief, more work. So I'm leaving out the K+, and permanganate is the effective ion. It's the oxidizer. And when hydrocarbons or alcohols are burned completely, the carbon goes to CO2. In the process of oxidizing the methanol, the permanganate is reduced to Mn+2. Which is this pale pink liquid you can see in the bottle on the far right. It's just barely pink, almost colorless. Now I'm going to show you a method for balancing redox equations that works with pretty much any reaction. Many times in your analytical classes you'll be required to balance a redox equation, and often you can do it by inspection if it's not difficult. But if it's anything difficult, like you'll find in organic, you'll want to use this method. It's basically a bookkeeping method, but it works quite nicely. There are, in fact, about 3 different methods I've seen, and I've tried them all, and this is by far and away the easiest method, and I promise you that. Before we do the process of balancing it, let's just look at it a bit. What's the oxidation state of manganese in permanganate? Do you recall it's +7, right? Oxygen's -2, and there's 4 of them. That makes -8. And the total charge is -1. Manganese is +7. So in this process, manganese is going from +7 to +2, and so it's going to be gaining 5 electrons, +5 electrons. It's being reduced. A gain of electrons is reduction. That's fine. And in the case of the carbon here, carbon is going from, well, let's say it's going to. This one's easy on the right. This will be +4 because oxygen's -2, and there's 2 of them. That's -4, and the total charge is 0, so carbon must be +4. How about in methanol? Hydrogen is be +1 because it's bonded to more electronegative atoms. Oxygen's -2. The same is true here. There's 3 hydrogens. So what must carbon be? If the total charge is going to be 0, carbon must be -2. To go from -2 to +4, carbon must be losing -6 electrons. A loss of electrons is oxidation. This is an example of a reaction that you could balance by inspection, as I'm doing here. Just to balance the electrons, you'd see that you would need 6 moles of permanganate, 6 times 5 is 30 electrons. For 5 moles of methanol, 5 times 6 is 30 electrons, and it's done. You could do this without this method, but I'm going to start here, and you will find that particularly in organic reactions where they have complicated organic molecules, it's virtually impossible to balance by inspection, so the method works in any case. So here is the method for doing that. Now the rules are listed on the previous page. I'll just tell you them and briefly write them as I show it to you. The first step is to break this into 2 half reactions, one for oxidation and one for reduction. So what's being oxidized and what's being reduced? Well, I think it's obvious from this that the permanganate is the oxidizer and it's being reduced. The methanol is being oxidized. So I'll write here methanol is being oxidized to CO2. Over here I'll write permanganate is being reduced to Mn plus 2. Now I'll just, as briefly as I can, I'll write up the rules as I go. So rule number 1 is you balance the atoms other than hydrogen and oxygen. Okay? So in the case of this oxidation half reaction, that would be carbon, and it's already balanced, so we can continue on. Rule number 2 is that we balance oxygen with water. Okay? You have to add water to balance the oxygens. You can't add O2. O2 is not in this reaction. That would be a different reaction entirely. The only way you can balance oxygen is with water, and there's always water in aqueous solution. So let's do that next. On the left I see 1 oxygen, on the right I see 2, so I have to add 1 oxygen to the left. I'm going to add it as water. This will be CH3OH plus H2O goes to CO2. Okay, our third rule is that we're going to balance hydrogen with H+. This reaction we're carrying out is done in acidic solution. It makes a difference as to how we treat it. So in acidic solution we have water and hydrogen ion, so we're going to balance our hydrogen with H+. And you can't add H2. You can't add hydrogen gas. It's hydrogen gas is a reducing agent. That's a different chemical, different reaction. All you have to work with for balancing is water and hydrogen ion in acidic solution. On the left we have 2 plus 4 is 6 hydrogen atoms. So we'll have to add 6 hydrogen ions on the right. And that's balanced now for mass. To balance for charge, we can only add negative charges. 0 on the left plus 6 on the right. How do we make them equal? If we add 6 negative charges on the right, 6 electrons, then the charge is 0 on both sides. So that is balanced for charge and mass. Do the same now for permanganate. First step is to balance the atoms other than hydrogen and oxygen, but manganese is balanced. The second step is to balance oxygen by adding water. There's 4 oxygens on the left. I'll add 4 H2O on the right. Oxygen is balanced. The third step is to balance hydrogen by adding H+. I now have 8 hydrogens on the right, so I will add 8 H+'s on the left. It's balanced for mass, now charge. This is not difficult, but be careful here. Students often get their charges in the wrong places. On the right side is plus 2. On the left side is plus 7. You can only add negative charges. So I'd have to add 5 negative charges, 5 electrons. I don't know why, but often students will add the electrons to the right-hand side here. But if you stop and think, if I added them over here, the total charge would be minus 3, and that would not equal plus 7. Furthermore, think of this. An oxidation, remember, is the loss of electrons, right? Leo. And so electrons must always appear on the right side because that's where they're being produced or lost. In a reduction reaction, which is the gain of electrons, GR as reduction, well, the electrons must always appear on the left-hand side because you're adding them, you're gaining them. So this is balanced for charge and mass as well. Now these will combine in a stoichiometric ratio such that the number of electrons gained is equal to the number of electrons lost. right? In acid-base reactions, we combine hydrogen ions with hydroxide ions. But in redox reactions, it's the number of electrons that have to balance. What's the lowest common multiple of 6 and 5? Well, it would be 6 and 5, right? If I multiply the oxidation reaction by 5, the reduction half reaction by 6, I'll have 30 electrons transferred in each case. When I multiply this out, I won't bother with the electrons. They will be balanced. I'm going to combine them together. This is 5H2O plus 5-methanol. Pick up the other left-hand side. That's 6 times 8 hydrogens is 48 H plus. And then 6 permanganates. I think that's all of it. Now the right-hand side will be 5 CO2 plus 30 H plus. The other right side will be 6 Mn plus 2. 6 times 4, 24 H2O. If I've done that carefully, that should be balanced. All I need to do is cancel any common species. So I see on the right I have 30 H plus that I can subtract from the left. I'll wind up with 18 H plus on the left. I can cancel 5 water from the left and take them away from 24. I'll have 19 water molecules on the right. And that's it. Not so bad, right? Balance for charge and mass. What this tells us is that if we want to oxidize methanol with permanganate to CO2, the stoichiometric ratio for this reaction is 6 moles of permanganate for every 5 moles of methanol. That's done in acidic solution. Sometimes redox reactions are carried out in basic solution. Take a look at the next example. I will explain what this MnO2 stuff is in just a moment. So in this second reaction, let's say we take ethanol. We'll go on one step higher. C2H5OH. And we'll oxidize it again with permanganate, MnO4 minus. This time we're going to do it in basic solution. In either neutral or basic solution, the product is different. Permanganate is not quite as strong an oxidizer, as you'll see. It still produces carbon dioxide. It's strong enough to do that, but itself is not completely reduced. It goes to MnO2. That's a solid. And it's that brown, gooey, gelatinous precipitate that I show you in the test tube. That's MnO2. In this case, the oxidation state of manganese, you can probably figure it out here. It's -4 for the oxygens, +4. So in this case, manganese went from +7 to +4. It only gained 3 electrons. So it's not quite as strong an oxidizer. It's still oxidation, but the product is different. Now don't be worried about memorizing the products. I'll give you the reagents and products. I want you to learn how to balance the equations. In the case of carbon, well, carbon ends at +4 as we saw before, but the starting oxidation number gets a little more complicated. And this is the very reason why we need a system like this, because balancing this by inspection gets really difficult. And ethanol is a simple compound. We could have much more complicated compounds than that. So let's go ahead with the process. The first step is to break this into 2 half reactions. One for oxidation, one for reduction. Again, for oxidation, it's the organic material, ethanol, ethyl alcohol that's being oxidized to CO2. For reduction, again, it's the oxidizer, permanganate ion, that's being reduced, but this time reduced to MnO2. I should mention, be really careful about the charges. You can't leave out charges. If you do, you'll go wrong, and it's important. All right, so the first step is to balance the atoms other than hydrogen and oxygen. In this case, they're not balanced. So I'm going to do that first. C2H5OH will produce 2 CO2. Now we carry on. We balance the oxygens by adding water. So on the right-hand side, I see 4 oxygens. On the left-hand side, I just see 1. That means I have to add 3 oxygens. I'm going to add them to the left side as water. Remember, you can't add oxygen. The next step is to balance the hydrogen with H+. Now you say, wait a minute, I thought this was basic solution. You're right. But we balance it as if it was in acidic solution, and we'll fix it later. And I promise this is way easier than learning a different set of rules for basic solution. I've tried it both ways. So let's pretend it's still an acidic solution. Only one set of rules to memorize this way. So we have 6 hydrogens plus 6 more is 12 hydrogens. We need to have 12 hydrogens as 12H+. Charge on the left is 0, charge on the right is plus 12. We add negative charges only, add 12 electrons. Okay, that looks all right. Now, if this was acidic solution, we'd be done. But it's not. It's basic solution, so we don't have any hydrogen ion. We have water and hydroxide. So what we do is we add as many hydroxides as there are hydrogen ions and combine them with the hydrogen ions to make an equivalent number of water. 12 hydroxides and 12 hydrogen ions makes 12 H2O. Now before I added those 12 hydroxides, my equation was balanced. But by adding the 12 hydroxides, I unbalanced it. So I have to make sure it's balanced. I need to add the same number of hydroxides to both sides. That's the only extra step we need. Now sometimes you can cancel, as in this case I have 3 waters that I can cancel or subtract here, and I'll wind up with 9H2O. I'm just going to rewrite this so it's easier to work with. So I'll have 12 hydroxide plus ethanol goes to 2 CO2 plus 9H2O plus 12 electrons. Let's try the reduction half reaction. Same process. The atoms other than hydrogen, oxygen, manganese, that's balanced, so let's move on to the next step. We balance the oxygen by adding water. I have 4 on the left and 2 on the right, so it looks like I have to add 2 oxygens as H2O. Next step is to balance hydrogen with H+. 4 on the right, let's put 4H+ on the left. Balance the charge. On the right it's nothing. On the left it's plus 3. That means I have to add 3 electrons. Now the left side is equal to 0, as is the right side. Be careful here. I see students often mix up here, putting electrons in the wrong places or miscounting. It's not hard, but it definitely takes care, and it's a mistake that I often make too if I'm just rushing. Okay, so this now is balanced for charge and mass, but remember, it's in basic solution. We do not have hydrogen ion present, so we're going to neutralize all of our hydrogen ions with an equivalent number of hydroxides and form that many waters. 4 hydroxides and 4 hydrogen ions makes 4H2O. And we have to make sure we add the same number of hydroxides to both sides, otherwise we have unbalanced our equation. If we can cancel some water, we do so, and it looks like we can again. Subtract 2 from both sides, leaving me with 2H2O. I'm going to rewrite this so it's tidier. 3 electrons plus 2 H2O plus permanganate ion goes to MnO2 plus 4OH minus. So the next step is to combine these two half reactions, but I have to do so in the stoichiometric ratio where the number of electrons gained is equal to the number of electrons lost. So I have 12 electrons and 3. The lowest common multiple is 12. If I multiply the right-hand equation by 4 and then combine them together, it should be okay. This is not difficult, but it just takes care. So I have, my left side is 12 hydroxide plus ethanol. Okay, the other left side, 4 times 2 is 8 H2O and 4 permanganate. All right, the right sides, I have 2 CO2 plus 9 H2O. And the other right side is 4 MnO2 plus 16 OH minus. So now I can just cancel anything that's on both sides, subtract 12 hydroxides, leaves me with 4 hydroxides on the right. I can cancel water, subtract 8 from both sides. I'm left with 1 on the right. I'm just going to rewrite this. Ethanol plus 4 permanganate ions goes to 2 CO2 plus 4 MnO2 plus H2O plus 4 hydroxides. So what this tells us is that if we want to oxidize ethanol with permanganate, we require 4 moles of permanganate for every 1 mole of ethanol. This is something we actually do. We do it in the analytical lab, we do it in the organic lab. So this process is something you really need to pick up on. And it usually takes some time, a few swings at it. I'd like to do one more example with you for some more practice. We'll up the scale a little bit further. This time we're going to use potassium dichromate as the oxidant. Notice that the chrome is in a high oxidation state because it's 7 oxygens in it, an oxidizer. It's reduced to chromium plus 3, which is this green color. And we'll use it to oxidize propanoate, which I'll give you the formula for, and you'll have to wait till organic class in the 3rd semester to learn more about what I'm talking about. So this is propanoate. It's C3 H5 O2 minus, reacts with dichromate ion Cr2O7 minus 2. We leave out the spectator ions because they just make it harder to balance. I'm going to do this one in basic solution, and it goes to chromium plus 3, the green stuff, and again the organic is oxidized to CO2. I'm going to break this into 2 half reactions for oxidation. The organic is being oxidized to CO2. Looks like I already wrote in the 3 for the CO2, sort of autonomically, apologies, but we'll leave it at that. And reduction is dichromate goes to Cr plus 3. It's in basic solution. Let's remember the rules. The first rule is to balance the atoms other than hydrogen and oxygen. I already did that for you. Carbon is balanced. Next we balance the oxygen by adding water. So here I'm going to add I see 6 oxygens on the right and only 2 on the left, so I'm going to add 4 oxygens as water, so 4 H2O. Next we're going to balance the hydrogen by adding H+. So I now have 8 plus 5 is 13 on the left. Looks like I need 13 H+ on the right. We'll fix the fact that it's in basic solution later. We need to balance the charge. I have -1 on the left and plus 13 on the right. How do I make them equal? Only by adding negative charges. I'd have to add negative charges to the right-hand side. This would be plus 14 electrons. That way the right side is -1. Remember, oxidation is loss of electrons, so your electrons have to always appear on the right-hand side because they're being lost or produced. That should be balanced for charge and mass. Now we have to neutralize the hydrogen ion with an equal number of hydroxides and make an equal number of water molecules, which is what they will do. We have to keep the equation balanced by adding the same number of hydroxide to both sides. On both sides we can cancel 4 waters. This reduces to 9. I'm going to rewrite this. So I have 13 hydroxides plus propanoate, C3H5O2 minus, goes to 3CO2 plus 9H2O plus 14 electrons. Let's try the other half reaction. The first step is to balance the atoms other than hydrogen and oxygen, which is chromium in this case, so I'll put 2Cr plus 3. The next step is to balance the oxygens by adding water. I'll need 7 water molecules on the right. Next we balance hydrogen by adding H+. I'll need 14 H+ on the left. Now be careful here. It's not hard, but it's tricky. We have plus 6 on the right and plus 12 on the left. How do we make these equal? We can only add negative charges. We can only add 6 electrons, right? 6 negative charges, and plus 12 makes plus 6, and the right side's plus 6. Most students, if they have a problem, it's usually in this part, so be careful with it. Right, so this should be balanced for charge and mass. Let's neutralize all of our hydrogen ions, because we're in basic solution, with an equal number of hydroxides and make that many water molecules. We'll add the same number of hydroxides to both sides. We'll cancel. Let's see, 7 water from both sides. Let me redraw this. 6 electrons plus 7 H2O plus Cr2O7 minus 2 goes to 2 Cr plus 3 plus 14 OH minus. Next step is to find the lowest common multiple of electrons. We have 14 on the left and 6 on the right. What's the lowest common multiple of 14 and 6? Well, if I double 14, that's 28. 6 does not divide evenly into it. But 14 times 3 is 42, and 6 divides evenly into it 7 times. So if I multiply the left equation by 3, that's 42 electrons. If I multiply the right equation by 7, that's 42 electrons, so that should work. So again, it's not difficult, but it requires some care. So 13 times 3 is 39 hydroxide plus 3 propanoates. Let's pick up the other left side. 7 times 7 is 49 H2O and 7 dichromates. Let's pick up the right side. I have 9 CO2, 27 H2O. The other right side, 7 times 2 is 14 Cr plus 3. And 14 times 7 is 70 plus 28 looks like 98 hydroxides. If I didn't miss anything, I can cancel common species. If I subtract 39 hydroxides from both sides, that leaves me with 59 hydroxides. 59 and 39 is 98, that's correct. And for water, I can subtract 27 from both sides, and 27 from 49 would be 22. I'm just going to rewrite this. I'll say 3 C3 H5O2, that's propanoate, plus 22 water molecules plus 7 dichromate goes to 9 CO2 plus 14 Cr plus 3 plus 59 hydroxide. What's this telling us? If we want to oxidize this propanoate with dichromate, we need 7 moles of dichromate for every 3 moles of propanoate, and there's the reaction in basic solution. To my knowledge, this method works with any redox reaction. It's not really very difficult. I admit it is tedious. It's easy to make a mistake if you're not careful. Take your time, take care. Please watch the video if you're at all unsure. You'll need to practice this. Certainly on the first test, you'll be balancing 1 or more redox equations. You'll have to do it in analytical and organic, so it's a skill you need to pick up, and you can with a bit of practice. And that'll be it for redox reactions.